All right, we'll do some more practice with refraction, then hopefully I'll show you something else involving refraction today as well in this video. So let's take just a basic refraction scenario again and warm up with that. So here we got a material, some kind of little boundary going on, something like that. And suppose over in here, let's see, we get some light going here. So light's coming in, something like this, then it's going to refract. Just from this picture, I know that the bottom material has a higher index than the top material because its angle is smaller measured from the normal. So I already know that. Okay, so let's see what we've got going on here. Let's say in the top part over here, let's say light is traveling at 1.76 times 10 to the 8 meters per second, and it's coming in. And let's say it's coming in at 50 degrees. And then it goes into the other material, and let's say the index for the second material over here, let's say it is 4.15, and I would like to know what is the angle in the second material. Okay, well, first thing I need to know is the index in the first material, so I can find that. So the index for my first material will be the speed of light in a vacuum divided by the speed, and I have the speed. So that's relatively straightforward to figure out. All I have to do is take the speed of light in a vacuum, the c value, and divide by the v, which I know. So if I divide those two out, I get a index of about 1.70. Okay, so a little bit higher than glass would be. All right, now that I have that, I can use my Snell's law. So sine theta 2 would be n1 sine theta 1 divided by n, put that n1 sine theta 1, that looks a little better, divided by n2, and then solve for n2. Don't forget to inverse sine it after you've calculated the values. Let's see, so that would give me about 18 degrees or so, something like that. Okay, so there's a little practice with Snell's law, and now let's see if I can show you something else kind of cool involving Snell's law and refraction. All right, so we're going to go back to the simulation that we've used before. Well, let's turn it on. All right, there's my waves going in, and what you guys did before is I would change the material down here, and it would cause refraction. Okay, so what we're going to do this time, though, is we're going to actually change the top material. We're going to make the bottom material is going to be air, and the top material is going to be the one with higher index. Now, if we do that, you can see it's a little bit different. It's the same type idea, but a little bit different. Now, the thing is, if I take my thing and I move it, one of the differences is that as I am lowering my light source, the beam on the top is getting closer to the surface. I'm going to change to a wave ray, a little bit less going area, that's a little better. My line is getting closer to the boundary, which makes sense. But the beam that's inside of the second material is actually getting closer to the boundary first. And if I get really, really close, eventually it actually just disappears. Now, this is what's called total internal reflection. Now, if I switch it around, that does not happen, because the angle here is always going to be smaller than this one. But if I start in a higher index material, it can actually happen. And this is called total internal reflection. And literally the light actually gets trapped inside the material and can't get out. Okay, you can actually see it. We've got here, this is the refracted stuff, this is the transmitted stuff, this is the reflected stuff, this is the partial reflection, this is that discontinuity thing that we talked about when we did like the simulations with that like little yellow rope and stuff like that. And you can see that the further I bring it down, the reflected part keeps getting darker and darker and darker because more is getting reflected, and eventually it's all being reflected and it actually is trapped inside of the material and the light can't actually get out. And this is what's called total internal reflection. So we're going to look at that a little bit today. It's a very specialized refraction. Okay, so we are going to look at what's called total internal reflection. And this is a specialized situation for refraction when you actually start on a higher index. So just sort of lay this out a little bit and see what's going on. So let's take some material. There's my boundary. Okay, and we have to start. You have to start in the higher index material for this to work. All right, so we've got our beam coming in, something like this, and let's say it refracts. All right, so no big deal. So let's sort of lay things out a little bit though. This is a higher index and this is a lower index, could be air or something like that. And we'd have our angle something like this. Okay, now as I move this one down, this beam is going to move up, and this one here actually hits that boundary first. And when that happens, the light will no longer go through, it'll just bounce back, and that's that total internal reflection. Now let's idealize this a little bit and label a couple things. That instant before it switches and starts reflecting, it's sort of technically going straight across like this, and the angle would be 90 degrees. We'd have the angle here, and that would be 90 degrees before it flips. And if we apply Snell's law to that, we can actually work with this a little bit. You guys have before n1 sine theta 1 is equal to n2 sine theta 2. And the specialization comes with that second angle when it's actually at 90 degrees. So if we make that 90 degrees, but the sine of 90 degrees, this right here, the sine of 90 degrees is equal to 1. So that term actually sort of disappears. It's just equal to 1. Now, this is a very special angle. This is then what's called the critical angle, because that is the angle you have to come in at in order to make this equal to 90 degrees to make the whole thing actually work. So n1 sine theta c for critical is equal to n2, and then that last part is just equal to 1, so we don't need to write it. If we arrange this, sine theta c is equal to n2 divided by n1. So what you can do is you can actually find the critical angle between any two materials you want by doing n2 divided by n1 and then just inverse sining it. And you can find out what angle you could actually go up to before it actually gets trapped in the material. Now just from this alone, mathematically, sine theta is always a decimal. So n2 divided by n1 has to be a decimal less than 1. Sine theta can't be bigger than 1. So this tells you the n1 has to be larger. There's no option. And that's why you have to start in the higher index material, otherwise it doesn't work. There's no critical angle when you're starting in a lower index material. It only exists if you start in a higher index material. That's the rule, so to speak. So light can always go from air to water, but light can't always get out of water and actually go to the air. Okay, so that's why, if we sort of sketch things out here a little bit, suppose you've got like a dock or something like that, and you've got water. We'll draw some nice water here, some water, and then underneath the water, you know, you've got the shore and stuff, then there's a whole bunch of stuff at the bottom underneath the water. And if you are standing here and you're looking into the water, if you look into the water, you can always see what's at the bottom right off the dock. There's like a rock down here, something like that. You can see that rock no problem because that light comes from the rock. It goes basically straight up and you can actually see it. If you look a little bit further out, you can see other stuff. Okay, so maybe there's like a little tiny fishy over here or something like that. No big deal. There's my little fishy. You may be able to see the fish because the light from the fish hits the actual boundary. It would actually refract to your eye. Okay, so it actually would change direction a little bit to your eye, and that's why you'd actually see the fish a little bit further out because we trace light back in a straight line. But if we keep on going further out, maybe there's a, I don't know, maybe there's like a little crab over here or something like that, a little pinchy crab. There's my little crab. Okay, you might not be able to see the crab because when the light is trying to get from the crab to you, if it is past the critical angle, instead of the light refracting it to you, the light will actually bounce back. Okay, that's total internal reflection. That's why when you're standing on a dock and you're at like the lake or a pool or something like that, if you look close to you, you can see into the water. But as you look further and further and further out in the water, you can't see into the water anymore. You can only see the reflection of the sky, the other shore, whatever other stuff is out there, because the light that is beneath the water, it might be trying to get to you, but it can't get to you because it's past critical angle and there's total internal reflection. It's kind of cool because if you'd actually go down here, you're swimming down here, there's you swimming down here, and if you actually looked up at the water here, you could actually see a reflection of the crab at that location, because the surface of the water then acts like a mirror, and if you actually looked up here, you would actually see the crab because the light is reflecting from the crab up here, bouncing off to where you are. Okay, so sometimes if you're actually in a pool, like a large pool, and you're in the shallow end, you go underneath the water, and you look at the water towards the deep end, the surface of the water, if there's one of those drainage hole cover things, something dark at the bottom of the deep end, sometimes you can see an eerie reflection of it on the surface of the pool when you're underneath the water towards the deep end. Okay, so for example, if we took water and air, which of course that's really, really common, if we did the sine theta c and we did the n for air divided by the n for water, and you actually calculate the critical angle for air to water, you can see the angle that you'd actually need. And if we do that, we should get around 48.8 degrees. That's a critical angle between air and water. So if this crab's light is going this way and it's past like 48, 49 degrees, it's getting trapped, it's not going inside. It can't get out. It gets trapped. It's not going anywhere. And that's what critical angle is about. And this is actually used for a variety of different things, actually. Whether you realize or not, it's kind of cool how this stuff actually works. So, for example, if we look at critical angle type stuff, it's used for tons and tons and tons of different stuff. Probably one of the oldest applications of it. This is why gems, more specifically diamonds, actually sparkle. Because if you take a diamond and you sort of analyze it, diamonds have an index. The index for diamonds is around 2.42. It's relatively high. So light can always get into a diamond, but sometimes it can't get out, which means it bounces around. And diamonds are cut in certain ways to trap light, so then when it does actually get released, it's really, really, really concentrated. So they don't just cut diamonds randomly, and a lot of other gems, they do the same type of thing. They cut them to trap light really, really well. So when it gets released, it makes them so brilliant, and that's why gems and diamonds sparkle. More recent, more modern type thing is fiber optics. If you got like fiber optic cables, and fiber optic cables work by sending light into one end for digital signal, and as the signal goes across, it hits the light hits the side, and it bounces and it bounces and it bounces until it hits the other end and gets out. So this is how fiber optics works. And of course, fiber optics are used for so much in terms of telecommunications and digital signals for computers and home theater systems and that type of stuff. So fiber optics actually trap the light in order to send signals, and that's why if you use fiber optics for your stereos and receivers and home theaters, stuff that your Blu-ray players, your Xbox, whatever, there's a little thing that you plug into the back and you'll see it glowing red, and that's the red signal light that's actually flashing on and off unbelievably quickly in order to make it work. So that is how fiber optics work. That's why gems sparkle the way they do. That's how fiber optics works, and there's tons of other things that critical angle is actually used for. And you've seen it your entire life. Stand on the edge of a pool, a lake. You've been seeing it cajillions of times, but now you have a little idea of how it actually is used. And these are just a couple applications for it.